Okay, we're cooking. If you have glare, you can hit the third white button down. All right. What was the homework? 117 and 1.17. Ninja. Ha ha! All right. So we're writing a function. Oh, this is only a 1-star problem. So was this homework too easy too?
This one wasn't bad.
No, that one wasn't.
All right. So we're writing a function called down that takes a list as a parameter. Shut up! Takes a list as a parameter, wraps parentheses around each top level element of the list. Interestingly, did I show you guys the map function last time?
You did.
Oh, so well, let's solve it with that real quick so you can just be sad. So we'll define down to be a lambda that takes in a list, and this guy will map the function list across list. So that's that. That's that one. So if we just take their thing here.
That's not as fun. It's not nearly as fun.
Is that what you...
What is that? That's like one of the symbols on the Stargate.
Wait, so you can use emojis in this?
No, that was me trying to paste that in, but I did the paste and match format shortcut, thinking that maybe it would fix the little single quote thing.
Nope.
Yeah, so there's that guy. Is that the right answer? All right, so obviously that's perfectly clear, right? So let me just explain this real quick, just in case. And I think I said last time when I taught you map, I said I'm not encouraging you to use map yet, right? Because so far every single time you've seen me use map, it probably looks a little bit like magic, because it's doing some stuff. Don't use it. Just see that it makes some things a lot easier. So there's already a built-in function in Scheme called list that will make something a list. So if I say list 1, that will give me the list version of 1. So I'm saying what map does is it takes a function that takes one parameter and it applies it, and then the second parameter is a list. And what it does is it applies this function to each individual element of this list. So it's going to apply the list function to 1, the list function to 2, the list function to 3, producing the list 1, 2, 3. Well, the list containing the list 1, the list 2, the list 3. Make sense? All right, so that's what this guy does. So let's call it down, cool kids. And then we'll write a new version of this. So define down to be a lambda that takes a list as a parameter. And we're going to go back. Remember last time we were kind of focusing on this idea of patterns, right? So we're going to go through every element of our list, and we're going to be building up a new list. Correct? Okay, so what we're going to do is we're going to ask the question if null list. If I'm out of stuff to look at, that means I'm done. And since we're building a new list, we're probably using cons. And cons needs the final parameter to be a list. So if I'm done looking at stuff, I'll boil down to the empty list. Otherwise, I want to construct a new list. What list? I want to construct the list that has something done to the car of list. What am I doing to the car of list? You could do this a couple different ways. You can either call the list function on that onto the down of cdr LST. So that's one version of down. What?
I'm concerned because this is scarily similar to what I wrote.
Well,
Good.
well, yeah, isn't that good?
Yeah, I'm concerned that I got it so close to what you're doing.
Well, I cheated off your homework.
Oh.
That's what I always do before class. I go and look at all the assignments that were. It's like, okay, I'm about to go in front of a live audience, and I need to make myself look smart. So I need to go through all these assignments, and I need to see which one looks most competent. All right, so there's that guy. Now, let's assume that you didn't know about the list function. Okay, because the list function it's not one of our, well, it sort of kind of is a primitive, but let's say you didn't know about that, because one of the reasons we use scheme in here is because it's a very simplistic language. So we're trying to solve almost all the problems in terms of really cons, cars, coulders, and like if statements, that kind of stuff, right? So let's say we didn't know about lists. So what we would probably do is we want to construct a list out of the car of that list and the empty list. That's effectively what the list function does. So if we were writing our own list function, define cool list. This would be a lambda that takes in a, let's call it cool listify. Ha! Okay, this guy would take in an element, and what we would do is we would cons that element onto the empty list. That's effectively what the list function is, right? Just, it's already built into scheme because it's something we might do often, right? Like I got something, I need to make it a list. But an important piece of the pattern there is to think about when I say we got something. Because one of the things coming from a procedural or an object-oriented language that you're probably still struggling with is when you take the car of a list, let's say, and I say, what is that? You want it to be like, oh, it's a number, or it's a string, or it's something else, instead of just saying, it's an element. It's something. The car of the list is the first element of that list, whatever that animal is. That make sense? It could be a function. I could have a list. I think, did I give you an example of something like that last class? I could have a list with a bunch of lambdas in it. Functions are way scarier than like numbers. Like I could have the number 3, or I can have like a lambda function that takes 14 parameters and, solves the meaning of life. Okay? But I could have a list of those if I wanted to. And the car of that list would be a function that takes 14 parameters and solves the meaning of life. That make sense? All right, so we're almost retraining our mind to think about things in more generic terms. All right, so this would be our cool listify thing. So if we wanted to use that guy, we would do that. And there's the same result. All right, questions on any of that stuff? All right, so was that the hard one, or was the other one the hard one?
The other one was the hard one.
Oy. Did you get that one right too? Because I only looked at your assignment. I was really struggling. I was running out of time. Did you even turn your assignment in?
I think I got
I just want to put this out there. It is somewhat common for him to do like a really good assignment and then just not turn it in. And like 4 weeks later, he's like, oh man, I did this. I promise it's in this folder, but yeah, Blackboard and me just kind of not a thing. I wish I was kidding. This is like almost like a consistent issue every single semester. It's like, look, I'll listen to your assignments. I'll listen to your lectures. I'll do your homework. I'm not turning it in. Like, what do you want me to do? Again, if only I wasn't kidding. It is really funny, actually. So swapper, what does this guy do? Swapper takes in a symbol and another symbol and a list of symbols. And it returns a list. Hold on, left eye's not working again. 1 second. Returns a list the same as S-list, but with all occurrences of S1 replaced by S2 and all occurrences of S2 replaced by S1. All right, so we have our pattern where we're going to go through every element of a list, right? and we're building up a new list. We're going to ask some questions about those elements in the list. So let's start off with our initial pattern. Define swapper. What's funny is we could actually do another map on this one if we wanted to. We could just map a lambda that does the, if you want to see that here, let's see. Let's call this, we'll say define chooser. Actually, can we do that? We can do a map, but not in the context of what you already know. We haven't done lets yet, so you can't create a local environment, so we're not going to do that. Because at some point I'm going to need access to S1 and S2. I'm going to need to be able to ask the question, is this guy equal to S1? If it is, replace it with S2. Is this guy equal to S2? If it is, replace it with S1. Otherwise, just keep it.
Okay. I don't know what you're going to try doing conversion.
This is going to be awesome.
We're not there yet.
Yeah. I'll highlight the part of the code once we're done that I would have mapped across everything. All right, so we're going to do normal plain Jane swapper. We're going to go through a list of symbols, an S list. All right, and what is a list of symbols? Don't they define that in the book at some point? This might come down to what V had asked me about. Are we going to talk about grammars, right? List of symbol. List of symbols. Here's list of int. List of int. S list. Here's a list of symbols. All right. So let's talk about. This is actually cooler than I thought. So let's talk about grammars. So this guy is a grammar. First of all, and we've read about grammars, but maybe didn't know what that meant. Is that a fair assessment? Okay, because this book is really made for children, like ages 3 and below. Okay, and this kind of goes back to the whole thing. Human beings are so good at solving problems, we've forgotten how to articulate them. So we don't remember the crap we read when we were 3. We had like the books with the puzzles in them. You like take the little piece out and you did you have those puzzle books, or you probably did? Your books were on iPad and stuff.
No.
All right, so a grammar is the definition for a language. All right, so if I were to explain like the grammar of the decimal number system, right? The decimal number system says that decimal numbers contain the symbols 0 through 9. And every number in the decimal number system has at least one of those symbols, right? So for decimal numbers, we would have 0 through 9 here with a little plus sign after it, which means at least one. We would probably call it decimal number, or decimal, we call this a digit. Let me actually put this in the slide so you can see this. We'll call this decimal grammar. All right, so we're going to say that a decimal, what's the book use? That guy? Yeah. So this is just a funky way of saying equals. It's just a stupid symbol, don't worry about it. So decimal is going to be, since scheme is always lists of things, we'll go ahead and say our decimal numbers live inside of a list. Whatever. So we're going to have a list containing one or more digits. Where a digit is in the set 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's one of those guys. You could say it's a 0, or do they use the vertical bar for their ors? Yeah, they do. or 1, or 2, or 3, or ... or 9. That's the grammar for decimal numbers. We might think it's weird to have a decimal number start with a 0, but it technically isn't broken. It's not an illegal decimal number. Like the number 123 could be 0, 1, 2, 3. That's still the number 123. It just looks funky, right? So we have at least, it's not a decimal number unless we have at least one of the numbers 0 through 9. But then we can have more of those, right? Okay, so this is the grammar for decimal numbers. And we're all comfortable with what a decimal number is. 126, 13, 2989. What's that? Why is that a fun number? 2989.
Well, that's bad, right?
It is bad. 2989 decimals equal to bad in hexadecimal. Favorite hexadecimal number?
Not dead beef.
That's my new favorite hexadecimal. Man, he's Appel's on a roll today. All right, so do we kind of get what a grammar is? It defines in like this like scientific formal way what the contents of a language is. Now remember, what's the goal of this class? Is we're building a programming language, right? So do you think like if we took a language like Java or we took a language like C++, could we write a grammar for Java? Yeah, it'd be a couple more lines than this, right? Because there's a lot of stuff in Java. You'd have a grammar for statements, and we'd have if statements. We'd have else statements. We'd have for statements, while statements, do while statements. We'd have grammars for all those different things, but not everything's a statement. Sometimes we have expressions like Boolean expressions. So you have different kinds of expressions. Some of them are Boolean expressions. Some of them might be numeric expressions, like a num expression. Some of these things are going to come back to us here once we get a little bit deeper into the book. Go ahead.
So, just to get my mind straight, a grammar is like a list of expressions?
No.
No.
Grammar is the definition of a language. This is the language of decimal numbers, what I've put right here,
Okay.
because it's simple. The grammar for Java would be much scarier than this, because Java can't be described as just a collection of at least one digit. I mean, that's what this effectively says. This says that a decimal number is a collection of at least one digit, where our legal digits are 0 through 9.
This is more like a visual representation.
It's a formal representation of what the language of decimal numbers is. Where we can do the same thing in Java, we would just have a whole lot more lines, because Java is more complex than just decimal numbers. Go ahead.
And just to make you say the same thing a third time,
Mm-hmm.
this is just supposed to be a human shorthand for defining a language, and it's not supposed to be like valid scheme code or whatever.
Correct. This is not valid scheme code. Yeah, you should be able to take this and translate it into something else. It has nothing to do with scheme, other than the book is putting everything inside of lists, because scheme is a list thingy, right? Or a list-based language. So in our world, if we wrote a number, 123, that doesn't match this grammar. The grammar this matches is 1, 2, 3. That's a decimal number as defined by this grammar. If we were writing the human version of this guy, we would take these little list things off, and we'd say that. A decimal number is one or more digits. So as long as I put at least one of these guys and follow it up with any number of those guys, I have a decimal number. That is the language of decimal numbers. Make some sense? So this guy formally defines a language. So we go back to our book here. This is the formal definition of an S list. What is an S list? It is a list, that's where the parentheses come from, containing, whenever you see a little star here, it's called a Kleene star. A really funky way of saying 0 or more. That's what that says. So it is a list containing 0 or more of those guys. Now, what is an S expression? SX. It's one of these guys. This guy says 0 or more. So S list is a list containing 0 or more of these guys. Where in my example a few minutes ago, this decimal, if we go put the list thing back in here just so we're kind of consistent with our, what the book says. This is saying I have a list containing 0 or more, or the plus sign says 1 or more, at least 1. So we don't have a number if I have nothing. If I just point to the table here and says, is that a decimal number? You see nothing sitting there, it is not a decimal number. I'm going to have at least 1 digit laying here on the table. Potentially I can have a bunch more after it, but I have to have at least 1. But they're saying an S list doesn't actually have to have anything inside of it, which means that a legal S list is the empty list. Right? If you had a list containing nothing, that's an empty list. So a legal S list is the empty list. A legal S list is also a list containing exactly one S expression. What's an S expression? Well, it's either a symbol, so like an A or a B or a C, okay, so that's like a primitive, or it's another S list. That make sense? So this guy, an S list, is a collection of 0 or more symbols and S lists. So we have a list that has a bunch of stuff in it. Each of those things is either a symbol or it's another S list. And what's an S list? It's a list containing a bunch of things, where each of those things is either a symbol or an S list. And what's an S list? It's a collection of a bunch of things. Okay, so this is recursively defined. 0 or more expressions where an expression can be a symbol or another one of those guys. Make sense? Okay, so let's go and solve this guy. So now we know what an S list is. Swapper is going to be a lambda that's going to take in a what are the orders of parameters to take in an S list?
S2.
Okay, so the symbols, the swap symbols. So S1, S2, and an S list. Just those 3?
Yep.
Okay. And if we're matching, didn't they call it what did our book say? The book called it an S dash list. So here we'll just be very precise. It's an S list.
In the problem definition, he didn't use the dash.
Who do we match? Who do we match? All right, I'm gonna switch it. I don't want to write a dash. So S list. All right, and actually this is already written wrong. So there's my parameter list. That's my parameter list for the lambda. So swapper is going to be equal to a function. That function is going to take 3 parameters: a symbol, and an S list. And what I want to do is I want to go through every element of S list, and anytime I see a thing, a symbol from that S list that matches S1, I want to replace it with S2. Anytime I see a thing, a symbol from S list that has S2 in it, I want to replace it with S1. If it's not either of those, I just want to keep it. Make sense? And what am I ultimately doing? I am building a list. Same pattern as we had before. Building a list. Isn't that what I'm doing? I'm swapping S1 and S2?
I wasn't sure if it was the reverse way around, like 2 for 1, and it was 1 for 2.
What? 1.18? Is that
The
the...
way he defines it, yeah.
So A and D, so anytime I see an A, I should put a D there, and anytime I see a D, I should put an A there?
Yep.
Yeah, so I'm swapping those two. So an A became a D, there's the D. A D became an A, there's the A. Anything that's not an A or a D, just stay the same. Make sense? All right, so I am building a list. My output here is a list, right? I'm building one of those guys. How do we build lists? Cons builds lists for us. Okay, and we keep building lists until we run out of things, until we can't car things anymore, right? Okay, so we're going to ask that question if null car S list. If S list has nothing in it, I'm done. And if I was in the process of building a list, what do I return? The empty list. Cons needs a list is the final parameter. Have we seen this exact pattern before? It's going to come up a lot. Where we say, hey, I'm going to be building a new list. And when I run out of stuff to build, I need to kind of, as my death call. What was your number? Dead beef? Yeah, as our dead beef. That's bound to stick, pun intended. All right, so we'll return an empty list. Okay. Otherwise, what are we doing? Well, I'm going to look at the front of that list. I'm going to make a determination. I'm going to say this. If. Now, I know if I'm in this else, I know that I definitely can take the car of the list, right? So I'm going to say if the car of S list, I want to know, is that guy equivalent? If he's equal to S1, what do? I replace him with S2, right? That's what I do when it's equal to S1. So I'm going to cons, I'm constructing a list, S2 onto whatever swapper returns for S1, S2, and the cooter of S list. I found an S1. I'm going to make it an S2 and cons it onto whatever swapper returns, passing it my original two symbols that I'm trying to swap with each other and the rest of my S list. Go ahead.
Don't you have to use EQV instead of equals because equals only works for numbers?
Numbers, you're right. I do. Actually, you don't need EQV. There's actually 4 of them.
Okay.
You can get away with EQ.
Okay.
That guy. There's an equal, there's an EQ question mark, there's an EQV question mark, and then there's the full word equal with a question mark.
Didn't work quite right.
Well, equal should always work. It's just to text bone structure.
Okay.
You know, it can like compare functions to each other. All right, so I'm saying is this guy equal to this guy? If it is, I'm going to replace S1 with S2 and then call swapper again on the rest of my S list. Else, if. Now, had the book talked about cons yet? C-O-N-D?
Well, I think we talked
You
about
mentioned the big thing.
I talked about in class. Do you want to write this as a con or do you want to keep doing it as nested ifs?
I did mine as a con.
Okay. Okay, so let's do it as a con then, because that will definitely make this. Let's just go back to this. I'm going to say con. It's going to have the same stuff in there. I'm just turning it into a con. So if null S list boil down to the empty list, if car S list EQ S1 boil down to the, actually I'm going to kick it down a line here, boil down to the cons of S2 onto the swapper of S1, S2, cooter of S list. If EQ car S list is an S2, then I'm going to cons S1 onto the swapper of S1, S2, cooter of S list. All right, so this is the two parts of our con that are doing the swaps, right? If I found an S1, swap it to an S2. If I found an S2, swap it to an S1. If it's not an S1 and it's not an S2, it's one of two things. It's either just a symbol or it's an S list, right? So we could ask, is it a symbol? I think the book talks about the symbol predicate. So we have these things, these functions called predicates. Predicate is fancy name for a function that takes one parameter and returns a true or false. For example, symbol, a lot of times the predicates have a little question mark in the end of it, kind of a naming convention. Symbol for A would return true. Symbol for 2 would return false. Symbol for the list A, B, C would return false. That's a list, not a symbol. We also have a predicate called list. So predicate for list, if I gave it a 1, would return a false. List 1, 2, 3 would return a true. Make sense? So I could ask 2 different questions for my next little step. I could say, if it's a symbol, what do I do with it? Keep it. Okay, so I'm saying if this is the S list, if it's the empty list, I'm done. If the first element is S1, make it S2, call swapper again. If the first element is S2, make it S1, call swapper again. Else, if symbol car S list, if the first element is a symbol, then what am I going to do with it? I'm going to keep it. So I will cons car of S list onto swapper S1, S2, cooter of S list. Go ahead.
I got a question about cons. So like in like Java or C Sharp, when you do a bunch of if statements, if multiple of those are true, it'll do both of them. In this case, does it?
Only one fires.
Okay.
Yep.
Okay.
So really what you're talking about is like a switch statement
Yep.
in traditional programming languages, and going all the way back to the C programming language, switch statements, you would have had to put a break.
Yep.
You put a break statement in there that broke you out of the structure. Otherwise, you could hit multiple points. So the reason he's asking that question is this. Let's pretend like that didn't even exist. Let's just deal with the next 3 things here. Potentially, I can find the car of the list being S1. But it could also, well, it probably would also be a symbol. Does that make sense? So if it didn't work in the way I'm talking about, it would hit true here and hit true again here. The reason why it wouldn't be a problem here anyways is because ultimately the result, this boils down to a value. It's not like we're changing stuff and then continuing on through our program linearly. So almost the nature of a functional language makes it work in the way that it needs to work. But in a traditional high-level language, we have switch statements, which are kind of let's call it a convenience for a whole bunch of nested if statements. That's kind of what we're doing here anyways, right? And what it does is that after each of those conditionals, if you want to say, oh, if this fired, I'm done. I don't want to hit any of these other ones. You put a break statement in and that gets you out. You stop asking questions. You don't have to do that in Scheme. And I typically don't teach switch statements anymore because now you have pretty convenient ways of doing if, else if, and that kind of stuff without having, an if with an else, with an if inside of that, with an else, with an if inside of that, and all of a sudden you're indented 5,000 spaces. Now you can just have everything lined up to the left where it's just as good as a switch statement.
Fun fact, in Visual Studio C Sharp, it will actually tell you have an error if you do not put a break statement between your switches.
I'd be surprised if it gives you an error instead of a warning. Because it's not illegal to avoid the break.
But if I'm remembering correctly, it specifically highlights it in red.
Okay, interesting. Because there would be a situation where you might say, here's a series of events that might occur. Hit all the ones that might get hit, where you actually want it to check every one of the conditions. But that's not the case with scheme. All right, so if it's S1, replace it with S2. If it's S2, replace it with S1. If it's just a symbol, keep that symbol, don't swap anything, and call swapper again. Else, if it's not a symbol, it must be a what? Must be an S list specifically, right? Because that's what our language says. We can assume that S list is a legal S list. So if it's not a symbol, if I'm still kicking here, I must be dealing with an S list. And when I'm dealing with an S list, what do? How do I make sure, because I want to call swapper on S lists, right? So I'm going to cons swapper S1, S2 on the car of S list. That's what swapper does. Swapper operates on S lists, doesn't it?
Mm-hmm.
If I'm in this else here, the car of S list must be what kind of animal? An S list. Swapper works on S lists. So I'll go ahead and cons whatever swapper returns for the car of S list, which is an S list, onto swapper S1, S2 cooter. Of S list. Easy peasy. We don't even need to test it, do we? What's up?
Famous last words.
So here, we'll call swapper. And don't you wish it would just copy this right out of here so I don't have to type much? I've already typed enough, I feel.
Well, the author didn't insist on using backticks instead of single quotes. Then that's what
It's
he did.
probably the font is my guess.
I mean, probably.
So there's our swapper. A became D. D became A. Rest of it was fine. Here, this one's a little bit, this was the more complicated one, right? Let's do that one. Ninja. Okay, so we're looking for an X. An X should become a Y, but this was inside of an S list, so that's the list Y. Then the Y became an X. Then we had a list that started with a Z. We kept the Z. We had another list that had an X in it, but now that X became a Y. So is that the right output?
Well, I was gonna ask that too, because I was getting it where it was turning those into lists. So like, if we're supposed to replace the symbol Y in X, why is it turning it into the list Y? What it's supposed to do, because that's what it was doing for me too.
What are you talking about? Like this?
Where we just have the Y sitting in there.
This guy?
Yeah. And that's where, oh, no wait, that's working right. Never mind.
Yeah. Yeah, the Y is this guy right here.
Just an X, yeah.
Yeah.
Okay, never mind.
All right, so that the right answer? So we've exhaustively tested it for everything? How many of you are ticked off right now?
What was that?
No, how does it?
Like, how did you just write that with all those parentheses and not even have to test it? It's because I cheated off of Papel. All right.
This is an improved version now.
Oh, this one is the upgrade?
Yeah, because I used nested ifs.
Oh yeah. Well, nested ifs wouldn't have been so horrible here because we only had to go down 4 levels, but yeah, it would have. That's why I asked if you wanted to use a cond or not. This is all the same crap. It's fine. All right, so I can just delete this. You guys don't need this code. This is one of those situations where I put the tip jar. All right, so let me put this. All right, let's put this up on Slack. No exit. I like that one. Man, Appel, you're on a roll today. So what was this? 1.17 and 8 and 1.18 or 1.16 and 1.17?
17, 18.
7, 1.18. Okay. So we all can agree that the questions so far have just been too easy. Well, we should go up to a 2-star. That means it's harder. And the 3-star means it's unsolvable.
It just means it's unsolvable.
So, we're going to do 1.19 and we'll do 1.2. 1.20. So a 2-star and a 1-star. So here, let's just look at this real quick and I can give you a hint. So list set takes in a list, an N and an X, and this returns a list that is like this list, except that the nth element in the list, using zero-based indexing, so like an array, bucket, the very first bucket is bucket 0, second bucket is bucket 1, bucket 2, bucket 3. So the nth element using zero-based index becomes an X. So this is sort of kind of like Swapper, right? Where we're going through a list, we're building a new list. That new list is mostly identical to the original list. But the nth element should change from whatever it used to be to X. All right, you want a little hint for this one? I think we talked about append in class. Okay, append will help you deal with the rest of the list after you hit the nth element. Okay, so you'll have to figure out how do you count to the nth element. But once you've done your swap, your switcheroo, it's not a swap, it's a switcheroo. Yeah. Once you've done that, then you can you don't have to just keep going. You can just append the rest. Get it? All right. So that's 1.19, 1.20, count occurrences, S list, and now we should all be intimately familiar with S lists. We know exactly what those guys are now. All right, because now we know how to read grammars. Whew, I can give you some really hard questions now. All right, so this returns the number of occurrences of S and S lists. So the number of times this symbol occurs, pay attention here, anywhere in this S list. Remember, S lists are lists of symbols and S lists. So if we're looking for an X here, an X occurs once, twice, 3 times. But this one was found inside of an S list. This one was found inside of an S list, inside of an S list, inside of an S list. All right? Is 2 enough, or should I give you another 4?
I'll take 2.
Again, tip jar. All right, questions, comments, concerns, bribes. All right, for Monday, 1.18 and 1.19.